Hello everyone, welcome to the Lab 6 of EC 573 Advanced Embedded Logic Design Winter 2022 semester. In the first part of the Lab 6, we discuss about how to use the private timer and how to enable the interrupt in the private timer. In this part of the Lab 6, we will discuss about the importance of the Watchdog Timer and how it can be enabled in the Zynq SoC. So as discussed before, in our Zynq SoC, we have the two types of watchdog timer. One is the CPU specific watchdog timer and the second is the system watchdog timer. In this case, we are going to focus on the system watchdog timer. So before we go into the details, let's discuss some theory about what is the watchdog timer. So the watchdog, the name is very interesting. It is like you are watching the dog and you are trying to do something to avoid that, to make sure that you are safe from the dog, so you don't allow the dog to bite you. So most of the embedded system need to be self-reliant. It is not usually possible to wait for the manual reboot if the system hangs. So for example, there are many issues or many cases where your processor gets hang. So one option is that you manually switch off the system and switch it on so that it comes out of that error state. But in case of the embedded system, which are usually remote deployed, how this process can be automated? A watchdog timer is a hardware timer that automatically generates a system reset. It's a hardware timer. That means it is not a part of the processing system. It works independently. It automatically generates the reset system. Okay. It automatically generates the system reset if the main program neglects to periodically service it. So in this watchdog timer is designed such that it will periodically receive the signal from the processor. And then once it receives the signal from the processor that indicate that the processor is working fine, so it will restart the timing operation. But if it doesn't receive the signal from the processor, and then what will happen, watchdog timer will count to the lowest possible value. So it says 0, and that indicate that the processor has not serviced the watchdog timer. That means processor is either in the error status or there is some problem has happened. Then watchdog timer will enable the processor to come out of that state by generating the reset interrupt. So used to automatically reset the embedded device that hangs because of the software or the hardware fault. This is also known as a computer operating properly timer. Okay, COP timer. So it is the main aim is to make sure that your system is operating properly. So it is another name for the watchdog timer is the COP, that is the computer operating properly timer. The main program, which is our application program, typically has a loop that constantly goes through performing the various functions. So in your code, you will have the thing that you will have this while loop where it will keep on going through this while loop. The watchdog timer must be loaded with an initial value because watchdog timer is a sum counter which counts from some x value to 0. So that x value must be loaded such that the total interval, that total timeout of that watchdog timer is greater than the worst case delay through the main program. Since the processor is a sequential unit, it performs the instruction by instruction in the sequential manner. The total delay in executing that worst case delay in executing that loop the delay may change over the time. So we need to take into account the worst case delay, and we need to make sure that we set the watchdog timer which has the delay sufficiently larger than that x, so that the processor will get some time to service the watchdog timer. Each time it goes through the main loop, the code reset the watchdog timer, say at the beginning or at the end, and this is called the kicking or the feeding of the dog. Okay, so the process of restarting the watchdog timer or counter is sometimes called as the kicking the dog. The appropriate visual metaphor, okay, for that is that man being attacked by a vicious dog. If he keeps kicking the dog, Okay, then what will happen? It can't ever bite him. So it will making sure that the dog can't bite him, but he must keep kicking the dog at the regular interval to avoid a bite. Okay, so similarly, the software must keep on restarting the watchdog timer at the regular interval so that it will avoid the reset. If a fault occurs and then the main program does not get back to kick the watchdog timer or reset the watchdog timer before it reaches its minimum value, the watchdog timer will generate an interrupt which will eventually reset the processor. So watchdog timer enables the fault detection. Okay, it enables the fault detection on an unattended embedded device and attempt a corrective action with a reset. Okay, so it's a very important unit of an embedded system. And now when the reset happens, so if you want to know whether the reset has happened because of the watchdog timer or there was some other reason, there is a register which is called as a reset source identification register. Depending upon which bit is set, you will know whether the reset has happened because of some power failure or temperature failure or because of the watchdog. So this will help you in the debugging your system. So it has been quite popular, and it has been there are many instances which could have been avoided if the watchdog timer is used properly. For example, in one of the famous case, the NASA's Deep Space Probe's computer locked up with the thrust rocket firing. So this thruster rocket firing is a unit which keeps on firing the rocket so that the space will move into the particular direction with the appropriate speed. So it will keep on consuming the more and more fuel. So in the space, there is no one around to push the reset button or to take out of the battery to avoid this rocket firing. Okay, because this has happened because of some mistake. And if you want to send the signal from the ground station, there will be a significant latency. So by the time the ground controller realized the problem and sent a radio signal to force the hardware reset, the entire fuel was used and your mission failed. The processor had a watchdog timer, but it was not used. Watchdog timer would have likely detected the fault and shut down the rocket motors in order to save the mission. Okay, so in general, the speed with which a human operator might reset the system would be too slow to meet the uptime requirement of the application one, and that's why you should make sure that you make use of the watchdog timer to avoid certain such scenario. Even the fault can happen in the multiple scenarios. Even the momentary noise spikes in a power supply can lock up the processor occasionally. So such event will occur on the power grid multiple times. The spike is quite common, and your system will get hanged. In this case, watchdog timer provides a last line of defense to prevent the system failure with a minimum hardware cost, because it's a small hardware timer and it will take care of the resetting the system. However, if the watchdog to be effective, resetting must be considered within the overall software design. So you need to make sure that to avoid the fault reset at the regular interval, you need to make sure that in your software design, you should service the watchdog timer at the regular interval. And in order to service it, you need to know that how much delay in each loop of your application is there and what is the worst case delay. So designer must know what kind of things could go wrong with their software and ensure that the watchdog timer will detect them, if any. For example, in case of the ISR, right, usually unusual number of interrupts arrives during the one pass of the loop. So extra time space in the ISR is the time not spent in the executing the main loop. And what will happen? It will send us what will happen, the watchdog timer will expire and it will send the reset interrupt. So your main loop or some loop execution time may get affected by the how many how many calls to the sub function is being made. So you need to be aware about the worst call you need to be aware about the worst delay of the particular loop. Also, if suppose that the multiple interrupt happens when you are in the particular loop, you need to service those interrupts. That means you need to execute those ISR. So the more time you spend in the ISR, that means more time you are out of that main loop, and this will trigger the expiry of the watchdog timer. So you need to keep your ISR short. Also, you can then disable the nested interrupt so that one interrupt may not lead to the another interrupt and so on. So you need to take care of all these things while designing your embedded system. So when multitasking kernels are used, the deadlocks can occur. So you have the multiple cores, multiple processor, and you might happen that one core is waiting for another core or some external input. For example, the group of tasks might get stuck waiting on each other or some external signal that one of them needs, leaving the whole set of tasks hung indefinitely. If the faults are transient, if these are the one or two time fault, then the system may recover properly because of the watchdog time. But it shouldn't happen that watchdog timer at the regular interval keep on giving the reset to the system. System is coming out of the reset. Again, the watchdog timer reset is happening and so on. So it should not do. It should not be a. It should not happen at the regular interval. Okay. So we need to make sure that after certain number of watchdog reset, the system, we should stop the system to avoid the this in the cyclic mode. Okay. So however, failed hardware could lead to a system that constantly reset. So for this reason, it may be wise to count the number of watchdog induced reset and give up trying after the fixed number of failure. So watchdog will give you the reset, but it shouldn't happen that at regular interval watchdog is giving the reset, because this is not a good thing. So we should make sure that after the certain number of watchdog reset, we should debug the system, or we should make sure that the appropriate warnings are issued to the human controller. Okay, so as we discussed, there are two types of watchdog timer. One watchdog timer is in the CPU, which is the private watchdog timer, and one is in the system, which is the system level watchdog timer. So you can see that you will have the corresponding register. For example, if you're here, you can see that you have the watchdog load to load the watchdog timer, to know the current status of the watchdog timer, control register of the watchdog timer, interrupt enable, disable for the watchdog timer. Then once your watchdog reset happens and once your system gets powered down and again you restart the system, then you need to know what was the reason about the reset. Is it because of the watchdog timer or is it because of some other unit? Then you can use this corresponding register. Okay, and you have the option to disable the watchdog timer also, but you should avoid disabling it in your practical application. But we are not going to use this private watchdog timer. We are going to focus more on the system watchdog timer. So we'll discuss more about the system watchdog timer and how to configure it in our application. So in the Zynq SoC, there is a system watchdog timer. So in addition to the giving the reset to the processor or handling the failures in the processor, it also handles the catastrophic system failure, such as failure in the any PS part or the PLL failure. So that is the advantage of the system watchdog timer. So it takes care of the failure of the entire system. So unlike the private watchdog timer, the system watchdog timer can run off the clock from the external device or the PL. So the private watchdog timer can work only on the PS clock, that is the CPU 1X clock. Okay, but the system watchdog timer can work on that clock, or it can come from the any external clock or any clock from the PL, and it provide the reset output to the all other device. It can provide it to the PL, it can provide it to the peripheral, some external device, as well as to the PS. In case of the private watchdog timer, it is only providing the interrupt signal or the reset signal to the corresponding CPU core, but the system watchdog timer is a more general. It is the 24-bit counter. Okay, in the private one, it was 32-bit. This is the 24-bit counter with a clock input from PS or from the PL or from the external sources via multiplex input output. It generates the system interrupt as well as system reset for PS, PL, or peripheral for external design, external peripherals. So you can check out, you can configure the timeout range, like after what time the watchdog reset should watchdog reset should be generated. So this count you can configure in your program code that we are going to do. It can range from the 330 microsecond to the 687 seconds, okay, at 100 megahertz frequency. Also, you can once you generate the interrupt or reset, you can also configure the duration of that reset pulse or interrupt pulse. It can be 4, 8, 16 or 32 clock cycle. So you can also configure in your design. Okay, so watchdog timer configuration, again you will have the corresponding .h file. You need to look at the corresponding driver functions. You need to look at the corresponding register, control register, status register and interrupt register, and you need to do such settings. So you can see that this is the architecture of the watchdog timer, which is a system watchdog timer. You have the control logic, which generates the interrupt as well as reset signal based upon your counter status. It will also use to restart the counter, reset the counter. Then you have the prescaler. So if you have the input frequency, but you want to slow down it, you can use the additional prescaler. And this 24-bit counter generates the 0 signal when it reaches the 0 value. Okay, so signal restart causes the 24-bit counter to reload the appropriate control register value inside the counter and restart the counter. So whenever you send the restart to the watchdog timer, it will load that particular value, which is the load register or the control load register value inside the counter, and counter will start counting down from that value. Whenever you are using in the debugging mode, so in the debugging mode, you know that the CPU will stop working for that particular time when it reaches the debugging mode. It is make sure that the watchdog timer also stop during that time. Okay. The 0 mode register, again, it's some of the control register inside the watchdog timer. It controls the behavior of the system watchdog timer, which when its internal 24-bit counter reaches the 0. That means your watchdog timer has expired. Now, this 24-bit counter stays at 0 whenever it reaches the 0 until it is restarted and the asserts until it is restarted. So whenever it reaches the 0, it will stay at 0 until the watchdog timer is restarted by some unit, or you restart your board. And it will keep on asserting the 0 signal. So it will keep on asserting high on this 0 signal. Upon receiving this 0 signal, this control logic will assert the interrupt as well as the corresponding reset signal based upon the how you are going to configure this watchdog timer. The restart register is used to restart the counting process. The status register show whether the 24-bit counter reaches the 0 or not. So you need to make use of this register to get the corresponding functionality or to know the status of your watchdog timer. The prescaler blocks divide down the selected clock input. So if you want to slow down the clock, this prescaler can be used. Okay. Now, once the watchdog timer reset happens, and once you restart the board and once you configure the board, you want to know whether the reset has happened because of the watchdog or there was some other issue. So for that, you have the corresponding register which store the reason behind the reset. Okay. So the type of reset that last occurred is recorded and it is stored in the reboot status register. So it is one of the register inside the Zynq SoC. It also includes the other issues, like for example, during the booting process, if some error has happened, then it is also that error status is also there in this reboot status register. This register is accessible by a boot ROM. It is also accessible by a first stage bootloader, or it is also accessible via user code. So anybody can see the status register. By using the status register, we will know whether the reset has happened because of the power on reset, like when you switch off the board and switch it on, or because it happened because of the non-power of reset, like the watchdog reset, or there is some software generated reset has happened. Because of that, by using this register, you will find out the actual source of the your reset operation. Okay, so in the lab 2, what we are going to do, we are going to use both the timers. We are going to use the SU timers. Okay, we are going to make the lab slightly more complicated. So we are going to use the SU timer like we did in the lab part 1, and we are going to use the watchdog timer. So what we are going to use, when the SU timer generates the interrupt, it will generate only one interrupt. When you generate the interrupt, we will start the watchdog timer. And once the watchdog timer generates the interrupt, our board will get switch off. Then we will configure the board again and we'll read the status of that reboot register to know whether the reset has happened because of the watchdog or there was some other event. Okay, so we start the watchdog timer after the interrupt is received from the private timer. When the watchdog timer goes to 0, it will reset the PS. You can see that the blue LED which I have shown in the previous lab, it goes off on the Z board if you have physical access to the board, third board. Then we need to program the board again by our regular process, and we will we at the beginning of our main application code, we will read the status of that register, and from that we will know that whether the corresponding reset has happened because of the watchdog or whether the corresponding reset has happened because of some other unit. Okay, so the process remains the same. You configure the SU timer, configure the watchdog timer and load it. Then you wait for the set up the interrupt for the SU timer as well as watchdog timer. Write the ISR for both of them. ISR for the watchdog timer will be the empty one because we are not going to do anything. After you SU timer generate the ISR, we should generate a flag which will help us to start the watchdog timer. After starting the watchdog timer, application goes in the while one loop, like infinite loop. It will wait for the watchdog timer to expire and generate a reset. Your processor will get reset. Then your board will get switch off. Then you need to restart, you need to configure the board again by downloading the ELF and bitstream file and then sample the corresponding report register to know the status of your watchdog. Okay, so with this we have completed the discussion on the watchdog timer. Now we'll go to our lab session and we will see how we can verify the functionality of the watchdog timer. Okay, so let's start looking at the code for the watchdog timer. So you can see that in the watchdog timer code, I have included the additional file, which is the scu watchdog timer.h. New file we will be needing it. Okay, rest of the things will remain the same. Then this value is for the SU timer. We are not going to change it. And then for this value, it is the watchdog timer. The watchdog timer will be loaded with this value and it will count down from this value. Then in the case of the timer ISR, we are not going to change anything. We are just keeping the this flag is we are going to make it 1. Okay. In case of the watchdog timer, ISR is empty because we are not going to do it. After the watchdog timer reset happened, it is going to restart the processor. So we don't need to do anything. You can display some printf statement, but it is not needed. Then before going to the interrupt status, let's start with the main code. In the main code, again, we will configure the SU timer, the same process as we did in the previous case. Then we are going to, this is the optional step for the self test. This is for the SU private timer. Then same like we did for the SU timer private timer, we are going to do for the watchdog timer, we are going to configure the watchdog timer. Then, as I told you, when we will, at the beginning of our code, we will know whether the reset has happened in the previous case, if any, is because of the watchdog timer or with some other reason. So what we are going to do, we will check whether the watchdog timer has expired, the corresponding status bit. This doesn't get clean when the watchdog reset or watchdog reset happens. Okay, so we'll sample the status and we'll display it. Then we are going to load the watchdog timer. We have not started it. We are just going to load the watchdog timer. Then we are going to configure the interrupt. Here we are going to configure the interrupt for two, one for the SU timer and one for the your watchdog timer. So the process will remain the same. First we will configure the GIC. Then we'll configure the interrupt for the timer and private timer and the watchdog timer. Corresponding ISR are connected, and that the steps are remain the same. This is the additional step for the watchdog timer. Okay. After we'll configure the interrupt, then what will happen? First thing we are going to do is that we are going to start our regular private timer. Okay, so watchdog timers operate in the different mode, so we need to enable the watchdog mode in case of the watchdog timer so that it will generate the reset for the processor. So this is the additional process we need to make sure. Okay, so this is the watchdog mode. Then we will start our private timer. Okay, then I will load our private timer with the particular value. What here I have done, I have just accepted the input from the user so that on the UART terminal, when we enter the 1, we will start our private timer. Now the private timer will start. You can see based upon the user input. After the private timer will start, the private timer will count down to 0. It will generate the interrupt. After it generate the interrupt, we'll wait for that interrupt to happen. Once once the interrupt is generated, this flag is set to 1. That means we will print that the private timer interrupt is received. After this has happened, we will start the watchdog timer. Once the watchdog timer is started, we will wait in the while loop to processor reset to happen. Okay. So with this, we will now test it. So what we are going to do, we are going to test it on the hardware. Once we are going to test it on the hardware, what will happen? Your hardware will go into the reset state. Then we need to configure this board again remotely, so that we will know that we'll check the status of the watchdog timer, whether the reset has happened because of the watchdog or because of some other reason. And then we will remotely restart the board to indicate that now the reset has happened because of the actual restart. And you will see that when we will sample the status of the reset, it will show that the reset has happened because of the actual restart and not because of the power on, because of the watchdog reset. Okay, so let's test our design on the hardware. So we'll go to the debug, debug configuration. We'll check the watchdog timer code and then go to the debug option. Okay, so now I have started the JTAG terminal also. So now let's see what happens. I'll run the code. So you can see that the processor reset state is 0. That means the initial reset, whatever the reset has happened before this code runs was not because of the watchdog time. And now you can see that we need to enter 1 to start our private timer. So I'll enter 1. So you can see that we have received the private timer interrupt, which in turn enable the watchdog interrupt. Okay, so the now watchdog interrupt has might have happened, and that you will see on the board that your board has gone through the complete system on chip reset. Now what we'll do is that we need to program the code again to understand whether the reset has happened because of the watchdog or because of the some other reason. So I'll program the code again. And now at the beginning of the code, we are in the main code. If you see, we are checking the status of the watchdog timer. And now you will see that the status has been changed to 1 because the reset has happened because of the watchdog timer. So now we'll go again. We'll open the JTAG terminal, and now I'll run the code. And if you see the code, you can see that the processor reset state is 1 because the reset has happened because of the watchdog timer, because we are checking that the watchdog timer is expired and it is saying yes. Okay, and this will remain the yes till we switch off the system on chip and switch it on. We give the power on reset to the system. Other than that, this register will will remain 1. Okay, so now how to do it? In my case, I'll restart my remote hardware and then I'll run this code again. Okay, so the board has been restarted. So we'll just check the status now, whether the reset has happened because of the watchdog or because of the power on reset. Now it should show that the reset has happened because of the power on reset and not because of the watchdog timer. So you can see that processor reset state because of the watchdog is 0. That means the previous reset because of the board restart was happened because of the power on reset and not because of the watchdog. So this is how you can use the watchdog timer.